Welcome back. In the next couple of videos, we're going to try and work on the idea that we had in the previous video and refine it a little bit. So the idea that we had is to add some sort of artificial diffusion to our partial differential equation and solve this new partial differential equation with a finite element method. And then we have an artificial diffusion that is small enough such that the solution that we obtain actually looks quite a bit like the solution of the true partial differential equation. But due to this additional diffusion, we now get a finite element scheme that is actually stable. Now, towards the end of the last video, I said that there was actually a couple of points with this strategy that we typically don't like as numerical analysts. And this is what we'll try to remedy. And I've prepared some numerical examples that sort of illustrate some of these defects of the current strategy. So this was again our model problem. This is a slide that I showed last time as well. So we have a square with a circular hole, and we have an advection across the diagonal of the square. And we have certain boundary conditions across the sides, and then this would be the true solution that we would look at. With a certain choice for our advective vector of a magnitude of 1.8 and a diffusion of 0.02. Now we saw different convergence curves for different strategies. We looked at artificial diffusion, but the new experiments that I want to show you are these. And again, this is for the simple Galerkin approximation. So this would be a standard finite element method. And on the left, you now see the error that you would obtain if you would use this approach. Now let me actually check. So this would actually correspond with this data point here. So this blue line was without any artificial diffusion. This is the mesh that I'm using. So this is a standard finite element method, and then you would actually get an error that looks like this. So as you can see, the error here is of a magnitude of 4, whereas the boundary conditions in my solution are in between -1 and 1 here below my figure here. So the error of 4 is clearly even outside of the range of our complete solution field. And again, that's the point that we're trying to solve here, that we get these clearly unstable, oscillatory, useless solution fields by using a Galerkin approximation, a standard finite element method. So we said, well, what we're going to do is add this artificial diffusion, and a solution that we would obtain would look something like this. And again, this is still the error field. So now the error is between -1 and 1, right? So it's in the same range as the solution that we see here. And as you can see, the error kind of revolves around the boundary layers here. Now, one interesting thing to note already is that this error is consistently negative. We have a blue field all around. And it's pretty widespread. It's blue almost everywhere. There's just a few regions where we do not have an error. And that's sort of one of the first things that I would like to continue talking about as we're trying to improve upon our strategy. And I think the first thing we have to do is kind of think about this error field a little more and actually come up with some thoughts on what we want to obtain here. Because one of the things that we have to realize is that, well, we're dealing with a very coarse mesh, so we will make an error. So the question is, what kind of error are we happy with? Is this an error that we're happy with? And if not, then what would we like to be different? So the first thing that I'll do is I'll kind of draw a line across the diagonal, across the two diagonals of this square, and then we'll look at what the solution field looks like, and then we also look at what we might want our finite element solution to look like. So the first thing I'm going to do is go over this diagonal. So if you look at the true solution, then you see that across that diagonal we kind of run into two different boundary layers. So let me draw that. So the true solution of our model problem across that diagonal would look something like, well, we start with a value of -1, right? That was in the bottom left corner. Then we go across the diagonal, and it actually remains relatively static because I'm using a 0 right hand side. F is 0, so I get a solution that looks a lot like this. And at some point, it's hitting this boundary condition of 0 across that circle, which means that suddenly the solution is forced up. Yeah, so we get something like this. And then we get a solution of 0 here. Well, then there's a bit of a gap in our solution field there. And at some point we continue, but still at a value of 0. Then again, because the forcing is 0, there's still a relatively flat area. So we continue like this. And towards the end, we get a new boundary condition of 1. And we suddenly get this large, steep solution field again. Yeah, so this is the solution across, sorry, I have to mirror my hands, across this diagonal. So if we then think about a finite element solution of something like this, and maybe our mesh kind of looks like this. Well, there's no mesh here, right? There's a gap. But let's say I have one more element. One more node over there. And here I have a node as well. And all the way at the end I have a node as well. Okay, so then what is the best possible solution that we might find on a mesh that is so coarse, given that this is the true solution? Well, this is something that we also drew in the previous lecture. And this is still kind of the trivial conclusion. Yeah? The more interesting is actually going to be the other diagonal, because for this one it's pretty straightforward. If we have a flat solution, then we want to get a flat solution in our finite element mesh as well. And all the way towards the end in this last element, well, we don't want to get, we know that this solution at this node is set to here, right? So that's fixed, that's a boundary condition, which means that we want to get a solution that looks like that. Yeah, we want to get a solution that in the volume is correct, and well, in that last element in the boundary layer, well, that's going to be incorrect, but that's fine. We kind of know that that's going to be incorrect because we simply don't have the mesh resolution to capture that boundary layer. So this is the best solution that we can obtain, and that is the solution that we want to obtain. Same thing for here. Yeah, we get something like this. So we're making a mistake in the boundary layer, but that's fine. So let's also draw the corresponding error field. So we have pretty much a 0 error all the way across this part of our domain. And then we have towards the last, in the last element, we suddenly have a certain error. And if I define my error to be u true, so the true solution, or phi true, minus phi h, the finite element solution, then we get 0 everywhere over here. And here we get actually a negative field. Yeah, it would look something like that. Yeah, because the finite element solution is larger than the true solution. So we get a field like that. So this is going to be our error. Same thing over here. So we get negative fields here for our error. And in my picture here, those are supposed to be blue, right? The negative fields are blue. And indeed, that's what we see. Yeah, okay. So that's what we see. Across this diagonal, we get a pretty much close to 0, although not entirely 0, and that's one thing that we'll talk about. Across the volume, and then towards this boundary layer, we certainly get one layer of elements where we have this thick error, which is of the order of 1. That kind of makes sense as well, because if we look at how steep these layers are over here, then the error that we're making around here is pretty much the difference between this and this, which is also going to be of the order of 1. Right? So this makes sense. Okay, now let's look at the other diagonal. And as I kind of said already, this is going to be the interesting one. And let me move my diagonal up a little bit, and I'm going to cut across this section, because I think this is where we can learn something, across this section here. So that's the solution field around here. And I'm no longer interested in boundary layers, so let me talk about this transition region here. Yeah? So there's also a sort of a sharp layer in the interior here. Yeah? So let's focus on that one. So then my solution field, and don't mind the values right now, but my solution field is going to look something like this. Something like that. Let me try this. Let me try that again. So it's going to be relatively constant here. It's going to be relatively constant here and here. Okay, I'll try it one more time. Like this, like that, that. Yeah, I think that's something I'm happy with. Okay, so the solution that we're getting right now, again, is blue everywhere, which means that our error is negative everywhere, which means that our finite element solution is overshooting our true solution everywhere. So apparently, the solution that we're getting right now looks something like this. That kind of makes sense, right? We're dealing with this artificial diffusion. We're over smoothing everything. But is that a solution that we're happy with? And I would say, no, that's not a solution that we're happy with. So let's think about that. Let's think about the type of solution that we might actually want to have in this area. So you know what? I'll just copy this guy. I have to draw this again. So this is the solution that we obtained with artificial diffusion. So then let's again think about the solution that we might want to obtain. There we go. Again, let's draw a mesh. Something like this, maybe something like that. Now let's put one element in between there, one at the end, something like that. I don't know, something, I guess something like this. Okay, now clearly in this first element, the solution, we can represent the solution, so we want to represent the solution. So the solution that I would want to get looks like that. Now in the second element, well, I certainly don't want to do something like what we're seeing in this artificial diffusion, that we're suddenly going to jump upwards. No, I actually find that my solution is constant in most of my elements. So preferably I would use an element that looks more like that, right? That's a better representation of the true solution than the one up there. So then let me skip the next two elements and continue here. Here again, we would want to obtain a solution that we can obtain, right? So we want to get something that looks like that. And towards the end, also, we want to obtain a solution that looks like that. So only in that layer do we want to accept that we have to make an error, and not anywhere else. So then, across that layer, we might actually want to get something that looks like... It kind of depends on how we're drawing this, but maybe something like that, right? That's a nice representation of that layer. And same thing over here. Maybe not entirely. I don't know. Something like this. No, I feel like I'm overdoing this a little bit. I do not understand why I'm sometimes not allowed to change. So honestly, if anyone has an idea, please send me an email, because this is starting to get rather annoying. Why am I not allowed to change? No idea. I don't want to keep on writing with red now. I guess for now this works, but okay, and suddenly things aren't okay again. Okay, yeah. So yeah, let me now I can erase. Let me make this a little. Oh no. Yeah, let me make this a little bit less extreme. So in between here we still have this, but maybe here we kind of want to accept that we're going to smooth things a little bit. And then we get an error that looks maybe like that, right? Okay, I hope that's sufficiently clear on your screen as well. So then let's take a look at what this solution field, what kind of error field we get with something like that. So here the error is going to be 0, and actually up until here the error is roughly going to be 0. But then we're making a positive error, right? We're making now a positive error. A true solution is larger than the solution of our finite element scheme, so we get something like this. Now then we're making a negative error, and towards that last element, so that should actually go to here. I'll try and be a little bit more careful with the way that I'm drawing. So that's going to be there. This one is going to be here. And get something until there is going to be negative. Until here is again going to be positive. And then we get something that is 0 for a few elements until here. And then until here, this guy is positive, negative, and this one positive. Okay, so we get something that looks like that. Yeah, so what we want to have is something that's going to be in my color graph, in my error plot here. We want to have something that across that diagonal is going to be red, blue, red, and also on this side red, blue, red. And what we get is something that is blue everywhere, which means that we get an error that looks like the one over here, where we have pretty much a negative error all the way over our domain, right? That's what we have right now. So that gives me a very blue, a thick blue region across this line. That's what we have, and that's something that we don't want. So why is that happening? Well, again, we're adding artificial diffusion everywhere. So then we might ask ourselves the question, why are we adding artificial diffusion across that line? If we look at our advection vector is pointing across this diagonal. So why are we adding a diffusion across this line, this diagonal? Well, across this diagonal, we can almost think of the partial differential equation as a pure diffusion equation. And a pure diffusion equation is something that the finite element method is actually quite effective for. So it's really only across this diagonal where we have the advective direction that our partial differential equation becomes this advection diffusion equation. Across the other diagonal, it's a pure diffusion equation. So following that line of thought, we might actually only want to add diffusion across the diagonal, across the lines where our advection is acting. And that idea is to have now not only an artificial diffusion, but an artificial diffusion in this upwind direction. So that's what we'll try to do now. We're going to try to change our idea of adding this artificial diffusion, but now not in all directions, but only in the direction of the flow. So we're going to get actually an orthotropic diffusion, right? Right now we have an isotropic diffusion, something that diffuses in all directions. We want to make this an orthotropic diffusion. Okay, so that's the basic idea and basic motivation. Now, how do we go about doing this? To do this, we're going to have to use a little bit of tensor notation. So the diffusion term in general looks like this. We have the divergence. The divergence always acts on a vector field. So whatever is going to be in here is a vector field, something that involves the gradient of phi. Well, the gradient of phi is a vector field. So what I can put here is a scalar, and that's pretty much what we've done so far. But that's not what I have to do. I can also add actually a second order tensor. Because if I have a second order tensor that acts on a vector, then it produces a vector. And again, I can take the divergence of a vector. So just from that perspective, what we've done so far with the scalars would be to say that we have kappa, and also maybe our diffusion or artificial diffusion, acting on the identity second order tensor. Right, so this right hand side is the same thing as what we have here. I hope that's clear. But now it's of the form of what we see on the left here with a second order diffusion tensor. Now this is again isotropic, the identity tensor. We might want to do now something that is orthotropic. So let's try to draw this out. So, suppose that we have a certain advection vector that points across a certain direction. So this is going to be A. Then we might at this point create a reference frame with a certain normal and tangential basis vector, N and T. So in general, we can always write our identity tensor as a sum of bases as a tensor product, right? So EI tensor product EI, summed over all i's. So if we have in 2D, we would get E1 tensor product E1 plus E2 tensor product E2, and in 3D we would get additional terms there. And here the e's are our natural basis, but you could use any orthonormal basis, and this would produce this identity tensor. So in this reference frame, I might also write I as my normal tensor product normal plus tangential tensor product tangential, right? So that's the reference frame that I'm using right now. But I'm assuming that my normal and my tangential vectors all have a magnitude of 1, right? So norm of n is going to be 1, and also the norm of t is going to be equal to 1. So now it kind of maybe already becomes clear. What we want to do is we want to have that our original diffusion, well, that's the physical one, right? That's not something that we're going to change. So that one is allowed to act in the isotropic direction. But we want our artificial diffusion not to act in all directions, but only to act on this direction. So we're going to rewrite now a little bit. I'm going to say upwind artificial diffusion is where we have minus the divergence of our physical kappa times the identity, right? That's still isotropic. Plus now this artificial diffusion, but not also in an isotropic sense, but only on this n cross n. Or n tensor product n, I should say. That's a gradient of phi. So that will only add artificial diffusion in that in the direction of it's very awkward sometimes. That it's mirrored in the direction of the velocity. So now that's going to be a bit tricky, right? How do we now incorporate this into some sort of numerical approximation where we don't want to write the basis n, but we can actually do this quite straightforwardly because we know, well, n is going to be in the direction of a, so I'm simply going to say that n is going to be equal to a, well, normalized, so divided by the magnitude of a. Right, and we automatically now have something that we can substitute in there without having to somehow create an orthonormal basis. That's the only one that I want. So I get minus the divergence of kappa, still times the isotropic tensor, plus this artificial diffusion now of A cross A normalized. And if I may already rewrite this a little bit, and that's going to be the same thing as kappa star divided by the magnitude of A squared times A tensor product A. Was one bracket too many. Gradient of phi, closing bracket. This one is missing closing bracket. Okay. So then, how does this eventually show up in a weak formulation? Now remember, in the weak formulation, we multiply this by a test function, and we integrate over the domain, and we do integration by parts. And in the end, what we have is, so in the weak form, in the end what we get is an integral over our domain of our diffusion tensor acting on the gradient of phi dotted with the gradient of w, our test function. So I can split this, and I get, well, k times I times the gradient of phi. Well, that's simply again going to be k times the gradient of phi, right? So nothing changes there, and we also don't want anything to change there. So that's what we're happy with. This was still our original term, but now we get this new artificial diffusion term, which again is only acting in the streamline direction. Let me at this point rewrite this artificial diffusion kappa star divided by a square as tau. That's going to be what we will call our stabilization parameter. So in many different types of stabilized methods, you'll actually always find tau to be the parameter that they'll call the stabilization parameter. Although we're not there yet, but we're getting there. Then again, A, tensor product A, is the gradient of phi dotted with W. Now this is something that we can actually write out further. Because if you work out this tensor vector multiplication, this one, then you find that this is going to be equal to A dot the gradient of phi, which is a scalar, times A, which is a vector. So this is going to be the same thing, dotted with the gradient of W. Yeah, clearly because this was a second order tensor, this is a vector, so the result has to be a vector, and that's what we see in the bottom as well. So that means I can write this out one more time. And then we can actually see that we obtain a term that is quite nice looking, as A dot gradient of phi times A dot the gradient of W. Now, both of these are scalars. Right? So we have two scalars multiplied with one another. And again multiplied by a stabilization parameter now. Now why am I saying that this is quite a nice term? Well, in fact, this is one of the terms that we already have in our original weak statement, right? So I'm not sure if I have that one here. Yeah, this is pretty much this term over here. And so it actually fits quite nicely what we have already. So now we still are dealing with artificial diffusion, but we've manipulated our equations such that they only act in the streamline direction. So what have we gained with that? So this is artificial diffusion in the isotropic sense. Now I'm using the same value for the artificial diffusion. So I'm using the same value for kappa star, the one over here, for the next experiment, but now I'm using this term, right? So I'm using as tau, just to be very clear here, as tau, I'm still using the same kappa star divided by a square, and then I'm adding this new term in my bilinear form as opposed to simply upping the diffusion. And the solution that we get is something like this. So that is pretty much precisely what we said in the beginning, what we want to have. Right? So on the main diagonal, the picture on the left, that's something that we had, and that's something that we're relatively happy with. Along this diagonal, we accept that we make a zero error up until the point that we hit the boundary layer, and then suddenly we have to make a big error. Yeah, that's the picture on the left again. So that's something that we had, and that's something that we still have, although less extreme, right? We have much less of this thickening blue everywhere. The main thing that we're gaining is that across that other diagonal we get a picture that looks much more like what we anticipated here on the right. We have a reddish, bluish, reddish. Yeah, that's what we had here. Red, blue, red. That's what we wanted in terms of what we would expect a good solution to look like. rather than this solution up on the top here of the artificial diffusion where we have this huge big blue region, right? The one here. So with changing our artificial diffusion such that now it's only acting in this upwind sense, in this streamline sense, yeah, I think that's what I should say. I should say streamline diffusion, not necessarily upwind. Upwind is something that we'll see in a second. In a streamline sense, then we get an error graph which behaves pretty much exactly in the way that we want our error to behave, because that's kind of what we anticipate our optimal finite element solution to look like. So that's one thing that we fixed in this video, and I think that's what I'll stick with for now. We changed this isotropy of our artificial diffusion that acts everywhere now into something that only acts where we have a problem in the direction of the flow, and by doing so we're getting to solutions that we want to obtain. Now there's still some issues. The fact that we're still dealing with an artificial diffusion is something that we still don't quite like, and that's something that we'll try to fix in the next video. Okay, thank you for your attention.